Spring, right? I'm thinking climate change, I think prediction of that.
Arby's?
I don't keep up with
Welcome back. This is about as loud as I can talk today. I don't know why it hasn't gotten better, but it hasn't. Or you can just listen real close. You're sitting in the front, you shouldn't have a problem. I don't feel sick. I feel like I yelled a lot and lost my voice. So, yeah. Happy Groundhog Day, I always say that. Today we are going to, thanks again, we're going to do some practice problems. First things first, I want to actually show you how the first battery cell was made. I didn't try this ahead of time because I had a meeting all morning for my grant. It's actually still going on, I just left. You guys are more important. See, this is my actual job, that's my recreational job. So you guys get priority. So we're going to try to build the voltaic cell, actually a voltaic pile is what it's called, a little bit about the history of it, and then we'll do some practice problems, and then if there's time we'll get into talking about passives. Sound good? All right, I'm going to take off my hat. I don't know if you said no, but I wasn't going to.
Definitely not me.
So, I don't remember the dates exactly, but in our scientific past, there's a guy named, an Italian guy named Galvani. And Galvani did experiments with frogs. And he sent electrical currents through the legs of frogs and he would make these dead frog legs twitch, move. So he hypothesized that electricity had something to do with this life force, life energy of living things. And he could make a dead thing kind of reanimate. Which was one of the fundamental or underlying themes of Frankenstein, the book, Frankenstein, Mary Shelley's book. Now, another guy named Alessandro Volta, another Italian who was pretty well known in the scientific community of his time and area, he couldn't stand somebody else getting attention, so he said, no, this guy's totally wrong. And he wanted to prove it, so he started working on trying to make electrical impulses and things that weren't alive. So it wasn't just a life force, it was something else. Now, we do use in our living beings electrical impulses to send signals from point A to point B. That's how our muscles contract, that's how our synapses work. They use ionic channels to send sodium ions through our brain. Nerves use electrical impulses. So yeah, it is part of like life, but it's inherent to living things here on the planet Earth. But it's also something that is independent of living things, and that's one of the I guess, aspects or side effects of Volta being an arrogant jerk. But his experiment led to development of a battery, which led to much of the electrical understanding that we have gained over the years. So it works, at least in the case of his voltaic pile, with two different types of metals separated by some sort of material that would corrode those metals. And they corrode differently, which pulls electrons from one and puts them onto the other, which creates a difference in potential. We've been talking about what a difference in potential is over the last couple classes. Electric potential is the push for charges to move through a system. I brought a couple that we have already. These got corroded in my office over the last 6 months, so it's old. But let's see if there's any charge left on them. This device is a device you will be becoming familiar with in lab intimately. Your lab practical is going to be using this device. So I figured I'd talk to you a little bit about it here, and he'll talk to you a little bit about it over there, and you get it twice as many times that way. It's called a multimeter. Multi meaning many, meter meaning measurements. So it can measure a bunch of different stuff. Each of these sections in here, each of the sections that are labeled on the dial, are a different type of measurement you can do. That one right there? Volts. What about this one right here? You're kind of right. There's two different kinds of volts. One has a straight line next to it, the other has a squiggly line next to it. The one with the straight line is DC volts, DC standing for direct current. The one with the squiggly line is AC volts, alternating current, alternating squiggly line, right? Makes sense. This one right here, just the letter A, right? All right. So is that one right there. The letter A stands for amps. Amps is the unit for current. That's how much charge is moving from point A to point B. We're going to talk about that in some substantial detail coming up as we get into circuitry. Right, this one right here. It's the Greek letter omega. Good job. It's a capital Greek letter omega. It looks like a horseshoe. Like that. See it? Greek letter omega. That stands for the ohm. The ohm is a unit for resistance. No, we aren't quite to Ohm's law yet, but we will be. We'll be there soon. This one, capital F. We're going to talk about that. Hopefully, no, good guess though. Hopefully today we'll talk about that. It's the unit for capacitance. It's farads, named after Michael Faraday. Yeah, obviously. The one we're going to look at right now is the voltage, and specifically, well, you're right.
Never got to that one.
Well, talking about that one hurts a little bit. It's a little painful. Hertz is frequency, and that's something that is specific to AC. It's how often it oscillates back and forth. Alternating current oscillates from positives to negatives, and it happens at a specific rate. These lights are blinking at a rate of 60 hertz. So the electricity in the wall oscillates from positive to negative at a rate of 60 hertz. But we don't need to talk about that just yet. We will. The one, as I was saying, the one we were going to talk about today is volts, and specifically direct current volts. It's the one with a straight line next to it. It tells you the electrical potential difference between 2 points, a positive lead and a negative lead. The red one being the positive, the black one being the negative. If I touch the positive lead and the negative lead onto the positive and negative terminals of a battery, always requires one more hand than I possess. There we go. You can view my lap partner. Hold on to that. Hold it up. Kind of so people can see it. You can see it too. Are we getting a reading?
Yeah.
Yeah, 1.55, oh, 0.7.
If it's not quite stable, I'm not getting a really good connection.
1.5.
Like I said, it's a little corroded because it's been sitting on the shelf in my office for like 6 months. But that being said, it should be somewhere in the neighborhood of 1.5 volts.
Yeah.
So this battery's still good. Nice. What do we expect it to be?
1.5 volts confirmed.
1.5 volts. I also have this much smaller battery. You can let other people do it too. You get to have all the fun because you're right in the front.
Yeah, let someone else have some fun.
You want to hold on to that? If you need to move, you can move, or you can just take it. It's up to you. So I'm going to touch one side to this. Actually, you can help. You want to hold this battery?
Yeah.
Yep. And I'm going to touch one side of my multimeter to one side, the other side to the positive side. And what do we get? Oh, we got another 1.5 volt battery. It doesn't look the same, but it's still 1.5 volts. And it should say on here 1.5 volts. It does, tiny though. A little tiny print.
Oh.
Can you see 1.5 volts? It says 1.5 volts. You confirm? Okay. All right, awesome. So those are both 1.5 volts. They work a little different. One's big, one's small because they separate their charges differently. But they both have the same difference in potential between the terminals, the same push. If I hook them up to a circuit that has a known amount of resistance, you get the same current through it. You'll just get the current through it longer for the big battery. This one's really corroded. I really don't know if this one's going to work at all. We're going to give it a try. We got a positive and negative terminal.
Thank you.
We getting some voltage in? Are we getting it?
-1.
So when you see that, I don't know if you all saw it, it just went to, it didn't have numbers anymore, it just said 1, and then no numbers afterwards. That means that the scale I'm using isn't big enough. I'm going past the capability of the scale at this point in the dial. But luckily, where it says volts, it has a set of numbers that go all the way up to 1,000. And that's not 1,000 volts, it's at most going to be 9 volts, because it says it right on there, 9-volt battery. So I'm just going to turn the scale up, and I'm going to go from, it was on set to 2, which means the maximum measurement at that point is 2 volts. So I'm going to just turn the dial up to where it says 20, now I can go up to 20 volts. We're going to give it a try. What do we see?
-9.27 volts.
So it's negative because I guessed wrong. I couldn't remember which side was the positive and which side was the negative. I tried to guess, I guessed wrong. I put the positive terminal on the negative side of the battery. So I'm just going to flip it around and touch it on the other side. And we should get positive now.
Yep, 9.2.
Can you always just leave it like on the 1,000, or do you have to go to like the smallest?
Great question. If I go way up high, the number of sig figs that I get is going to be reduced. If I want the most accurate possible reading, I want the smallest possible scale that I can get. Otherwise, I'm going to lose detail, and the answer, it'll be noticeably wrong, like noticeably different. You'll make noticeable errors. So when you're doing your lab practical, you want to get it as accurate as you can. So it's not a bad idea to start at a big scale and work down until you get that 1. And then you say, oh, that's 1 too far, and you go back. Now, the more you do this, the better idea you're going to have what scale to start at. So you don't waste time working your way down. But if we go all the way up to the 1,000 and I try to get a measurement, it might not give me anything. 008, 003. It's really not very accurate because it's zoomed way out. So good question, but it doesn't automatically zoom in for you.
What if we do different?
Turn it to something else. Well, we can try to measure the resistance of this, but a resistor is a different device, so it won't give us any meaningful information. There is internal resistance in batteries, and we will talk about that in June.
Thanks.
You want to stick your tongue out? We can test it.
I'm just thinking outside of the box.
All right, those are ready-made batteries. I'm going to try to make my own. One of the ways batteries do what they do is they have chemicals inside that cause charges to be separated. We're going to put that on the outside, and I'm going to give this a try right here in front of you. I have copper pennies from before I believe 85, when they stopped using copper in the pennies. And I have galvanized zinc-coated washers. They're, I think, made out of steel on the inside, but they're coated with an anti-corrosive coating. The galvanization process is named after that dude Galvani that did the frog leg experiment that I mentioned like 10 minutes ago. So we're going to give this a go. I'm going to put one zinc-coated washer down. I'm going to put a piece of paper towel that has some vinegar on it. Vinegar is acidic. It's got salicylic acid on it. Or just acetic acid maybe. I don't remember. I'm not a chemist. Any chemist in the room know better than me? One of them's Tylenol, the other's in vinegar. I don't remember which one's which. So I'm going to put a little bit of a corrosive agent on it. I went rock climbing yesterday, and my forearms are really sore. So maybe I'm just super weak.
Did you climb super high?
No. I climbed moderately high and I get tired.
Good job.
There's a new rock climbing gym in here.
Yeah, we went to it.
I went to it too. Yeah. The vinegar serves as the quote-unquote battery acid. It might be too big. That's going to pull electrons off of one of these and put them onto the other. And if I did this right, this is what you think. Just like vinegar all day. You guys are worth it to me. You want to come up here and be my lab partner again?
Me?
Yeah. we're getting some voltage, about 0.6 volts.
More like 0.9.
Oh, even better.
Oh, it's really strong.
Yeah. So, 2 pieces of metal and some vinegar, we made a battery. If I add another layer, if I do this one more time, we should get double the amount of voltage. The key is they have to be separated. We can't have them overlapping. And they have to have that corrosive agent in the middle. With those 2 pennies and 2 pieces of zinc, we have more voltage than we have in this battery. That's kind of cool. I thought so. You're welcome. Good job, thanks, lab partner. There are tons of videos online about Volta, and you know what? I'm not going to put that back in.
Are you going to use that?
Just trick it.
Is that FSA?
I don't know, I stole it from chemists. It is. So I better not put the messy stuff back in. Chemists like their stuff pure. All right, so that's how you make a battery. Now you know, if you're ever in a zombie apocalypse and need to make a battery, you can do it.
It's not going to fit into the battery.
No, you have to do some wiring.
Yeah. So it's really not.
No, what?
It's not going to work. It's not usable.
Wait,
What?
just like,
Oh.
yeah.
You actually put inside batteries though.
Different batteries have different stuff inside. New batteries often are made out of lithium-ion batteries. Older rechargeable batteries are nickel cadmium batteries. I don't remember what these ones are. I learned it when I was in college, but it's pretty easy to find out. We're going to go over a few of them today. You can ask questions as we go, and if we need more, then ask those two. Then that's what we're doing next. Thank you. I told you to remind me. You remembered. Thank you very much. All right. As promised, let's do some practice problems talking about this concept of voltage, about potential difference. How do we define what voltage was? What was voltage again?
V equals EPE over Q.
So it's energy divided by, you said Q, which is charge. Energy per unit charge. Joules per coulomb. So looking at that, it's gonna take a second. I thought this was already on. Dr. Treese let me down.
He's cranking you on the ground.
I thought about, for the lesson today, doing that, and then doing something else, then doing that again. And just like every 10 minutes, coming back and doing the same now. But as funny as that joke would be to me, it would waste your time and more than me. I had to weigh the cost and the benefit. I have sent the gift that says it's Groundhog Day again from the movie Groundhog Day to my family like 7 times this morning.
Oh my God.
I think that's really fun. Good time now.
I just received that. I'm not even kidding. I just
Oh, really?
received that. Yeah.
Nice. That's awesome.
You don't care what,
Hey, all right, there we go.
you don't care what kills.
1
Have you
volt.
seen the Groundhog Day movie? He keeps waking up and saying it over and over again.
Oh, I thought you were why you kept the
1 joule per coulomb.
I haven't seen that movie, but I've heard.
We watched it in school.
It's classic. 1 volt is equal to 1 joule per coulomb. 1 joule is energy. Energy is equal to the work done. Work is equal to force times distance. So 1 joule is equal to the 1 of the unit for force times 1 of the unit for distance. What's the unit for force? Newton, and distance? Meters. So 1 joule is equal to 1 Newton times 1 meter. Okay, gotta fix the battery. It's so annoying. Why doesn't it just automatically fix this itself? I don't know. All right, cool. The voltage equals the, energy, like I said, I'm getting a little bit beside myself here. The notes I have are really, really, really small, and I'm like squinting at them and trying to talk to you, and I don't multitask well. So bear with me. I'll do better, I promise. Okay. Much appreciated. The electric field, similarly to energy per unit charge, it was force per unit charge, which is newtons per coulomb. And I can put these two things together. And if I take the voltage and I divide it by meters, I get volts per meter. And with a little bit of analysis, which your homework makes you do, that's what I was trying to get to. That's what printed really, really tiny, and the point I was trying to make. If I take this and divide by meters, I can get a distance from point A to point B for a difference in voltage. And that will give me, through unit analysis, this exact same thing. And that's what I'm going to show. 1 volt is the same as this. If I take that and divide by a distance from point A to point B, to find the difference in voltage from point A to point B. So from one terminal of the battery to the other, or from one spot under a charge to another spot on a charge. If I take the voltage difference between those two spots, dividing by that distance, I take this unit divided by meters, I get newtons per coulomb, and that newtons per coulomb is the unit for electric field. So there's a connection between voltage and electric field we haven't made yet. That was the point I was trying to make when I screwed up by reading a little print. So I'm going to say it again because I said it wrong the first time. So I'm hoping if I say it right twice, it'll make that mistake go away. 1 volt is 1 joule per coulomb. 1 joule is 1 newton times 1 meter. The unit for electric field is newtons per coulomb. So the connection here is the distance between two spots. If I'm looking at the difference between point A and point B, if I divide by that distance, if I divide the potential difference by the distance between them, I can get the electric field between those two spots. So the connection from electric field to voltage, you divide by meters.
Is it the electric field or the EP? Are they the same thing?
They aren't the same thing. They're not the same thing. And that was a mistake. That's what I said wrong the first time. So I apologize. That's my fault. A couple of your homework problems say find the electric field, and they give you a voltage and a distance between 2 points. How do we connect those two things? We use this. The electric field is going to be the volts divided by the meters. The potential difference divided by the distance between the points. Cassie, did that clarify? Okay. Well, the good news is I won't screw up the next class. The bad news is I got a lot more people in here that I screwed up. So, sorry. So, to connect these two things, I take my voltage equation, I divide by the meters. Volts divided by distance is going to equal the newtons per coulomb, which is the unit for electric field. Through a little bit of unit analysis, we can find this answer. One of the homework problems actually walks you through this process, so again, my bad, I read it wrong, but the good news is you get to practice it, and this is the homework problem. This is the question. You just put the units in the right spot and it walks you through that process. At the end of our last class, I gave you an equation. It looked like this. Voltage equals K times Q over R. That's for the voltage some distance from a point charge. This is what, Cassie, what you were talking about. So we get this equation from the electric potential energy divided by the charge. The initial definition of voltage was electric potential energy per unit charge. The equation I gave you for the electric potential energy, some distance from a point charge, was K Q over R. And if I take that and divide it by Q, Q cancels out, we get this equation, equals K Q over R. There are at least one, maybe two more problems that use this. And it's a pretty straightforward application of this equation. It says you're some distance away from a charge. What's the potential at that point? You know the distance, you know the charge, you can find the potential. One slightly more complicated problem is the one you were just asking me about. I don't have that one in my notes, but we can go over it anyway. I don't remember which problem it was, but it gives you a charge on one side, it gives you a charge on the other side, and it gives you a distance between those two charges. We have Q1, we have Q2, and we have some point in the middle. We know the distance between them. And it asks you to find the potential at that spot. Do you know what problem that one is? Number 9. It's number 9. The previous problems are a very simple application of the V equals KQ over R. This one's a slightly more complicated version because you have to do it twice. I believe it gives you some fraction. It says that the point in space is some fraction of the distance between them, right? I think the one that was on my sample was 3/4 of the way. Is that true? It says not drawn to scale. Is
Yeah,
that
I
how-
have, it says for me, point A between the two charges is D over 3.
So 1/3 of the way. D over 3 is same as saying 1/3. So 1/3 would be like here. So this would, whatever your D value is, this would be 1/3. D, and this would be 2/3. So you can find that, it's just a numerical value. They word it in kind of a confusing way,
Yeah,
but
that's
that's what it means. Mine was 3/4. It was 3D over 4. So it would be 75% of the way. So finding that distance is probably the hardest part once you know how to do this. It says find the potential at that spot. To find the potential at that spot, I have to find the potential due to this one, and I have to find the potential due to that one. To find the potential, we apply V equals K, Q over R, and we get a value, we get a number. If you know Q, which is given in the problem, and you know R, which is the distance, you can plug those in, and I can find the potential at that spot due to this charge. It'll be either positive or negative, depending on whether your charge is positive or negative. The positive and negative is important. It does not imply direction, but it does factor into the problem. It does tell us whether, relative to our 0 point, what the potential is. Whether it's a negative potential or a positive potential, that is important. Once I have that value, I write it down, I have it, I keep it. Now, I stop paying attention to that one for the time being. It's in my back pocket because I'm going to need it later. But I don't need it right now because I need to find the potential due to this one. I use the exact same equation. I know the distance, I know the charge. I apply K times Q over R for this distance and this charge. Again, positive, negative, it just depends on whether it's a positive or negative charge. It has nothing to do with direction. A little confusing because when we were doing fields and forces, direction was super important. And you had to conceptually understand that. For potential, it's a scalar quantity. Direction is not important, just whether it's positive or negative. Once I have calculated the potential due to this one and the potential due to that one, I just add them up. If one of them is negative, then I add it as a negative number. Let's say, for example, I'm just making something up here. Let's say this was negative 10, and then this one is 5. I add those two things together and I get -5 as my potential, and that's the answer. Make sense? Awesome. Yeah.
So for the Q, you wouldn't take the absolute value of it, you just take it.
You have to keep it positive in a given case. Before, we can deal with the direction separately.
Yeah.
Since this doesn't have direction, you can't do that anymore. Like most college students I work with, scalar quantities don't have any direction.
It's just getting lots or whatever.
I don't know.
We never.
Other questions about that? Go ahead,
Well,
Karen.
it's same problem. The second part is like find a point on the line where the electric potential is 0.
Yep.
Do you,
So the tricky part of this second half is the algebra. Not necessarily the physics part, the math part is a little tricky on that. So at some point that we don't know, some point in the middle, V is going to equal 0. V total is just going to be equal to V1 plus V2. Which would equal K times Q1 times divided by R1 plus K times Q2 divided by R2. This being R1, this being R2. So far, so good? It's the same thing I just told you before. We have some spot in the middle. We don't know exactly where. This is a distance R1, this is distance R2. They're both some fraction of this overall distance that we know. The total voltage, we just did this. We found voltage from number 1, we found voltage from number 2, we added them up. That's what we did last time. Still true. But now it's saying that spot that we don't know is going to give us a total voltage of 0.
so you put 0 in for V, and then you're solving for R.
Well, we have two unknowns. We can't really solve it with two unknowns. We only have one equation. If you have two unknowns, you need two equations at least, and we only have the one. So we have to find some way to get rid of one of those variables. So we have to put them in terms of something that we know. Yeah.
The first parentheses on the question says enter your answer as noted from Q1, so are we using?
So we want R1. R1 is the final answer. That's what it's asking for. It says, how far from R1 is it? That's what those parentheses are telling us. So if we're trying to find R1, and we know the distance D, we know how far it is total. What is R2 with respect to R1? What is R2 compared to R1, I guess? Like, how would you find, if you know D and you know R1, how would you find R2?
The distance that's given minus
Sure. If I take the total distance and subtract from it this distance, what do I have left? I have R2. So instead of R2, I can write, so instead of R2, I don't have to write R2, I can write D minus R1. D minus R1 is R2. Those are the same thing. Does that make sense to you? Not a huge conceptual leap, but one that you might not think to make, which is why I'm telling you now. How many unknowns we got? Well, Q1's given in the problem, Q2's given in the problem, K is constant, D is given in the problem, just R1. We know everything else. So at that point, it's just algebra. Tricky algebra, but algebra nonetheless. All right.
On question 2, it starts, it says to solve for seconds. How do you,
I have question 2 with me. Let me look. It's in tiny, tiny, minuscule print, so bear with me again. I don't want to screw up again, so I'm going to be particularly careful. All right, we're given battery. Oh, we're given wattage. Oh, okay. All right, that's important. is a watt? Other than a good football player? Best defensive player in the league. But what is a watt in physics class? It's a unit for something. Power. Power. What is power? Work or energy. Energy per unit time. Okay, cool. What kind of energy have we been talking about? Potential, specifically electrical potential. But it's still a type of energy, right? And this problem is talking about dissipating a certain amount of energy. Right? I think that's what it's asking. Again, tiny print. If you think I'm lying, I mean, in my defense, that's really small. Not yet, but yeah, right. If I keep doing tiny print like this, we have magnifying glasses in the optics lab. I should have brought some. I didn't realize it was this small. I printed it in class. So we're given the power. That's how fast the energy is being dissipated. We're given the voltage, which is the energy per unit charge. We're also given the number of electrons, which is the total amount of charge. From the number of electrons, we can figure out the total amount of charge, right? So let's do a little bit of analysis of our units. We know in this problem the power. So we got that. We also know the voltage. Voltage is energy per unit time. And we know the total amount of charge. Sorry, not time, charge. And we also do know the charge. That's given in the problem because we know the amount of charge per electron, we know the total number of electrons, so we can figure out how much charge moves. So we can use that information, just that, not knowing any equations, just knowing the units of these things, and we can figure out how to get the time from them. I've been talking too much, my voice is strained. Talk to the person next to you. Think about this and see if we can figure it out together.
Yeah, but like, what's that gonna take? So you gotta give them. So.
The only thing we did was walk, wasn't it work?
We did work. That was something that was doing a volt. I don't know.
We did some work.
You to get that. That's what you need.
That was work. So where's the walk?
Just now.
I know you did.
We didn't sure.
You didn't even plug it in.
I didn't think we did.
So that'd be E.
I mean, like, you plug it in.
Yeah.
Where you
What is phosphorus?
I just don't know what we get.
And for the transit. Yeah, modification. So just to make it negative, it asks you guys.
Like our company, like how like we had to. Well, that's what we did last semester. What? You're gonna tell her now. I don't need to do it.
I know, and every single one of them. And I started getting upset and started second guess my son was like, wait, is that how you spell it? Like in this context?
Dude, your chance. Literally.
That was the word for this problem. What do you mean?
Where is it? So,
You were
Yeah, I've seen her once.
I love that though.
I didn't even know who she was.
Yeah, I didn't know what she looked like, so she gave me.
All right, we have a solution. Fire away.
So
have the first equation.
Okay, I handed you mine because I thought you.
So we have this first equation here, which we're gonna use second. So first we have this right here, we need to plug in, but we don't have Q. So we're gonna take the amount of electrons that you have, times 1.602 times 10 to the negative 19 to get the Q. So plug that in there. And then we're given the volts, which you can plug into V, and then solve algebraically. X equals 80.0199 joules, or whatever your number is. So we have this number now. We can plug it into the power equation. So it's going to go right there. And then we're given the watts, which is equivalent to power. So plug it in there, and then solve algebraically to get the time, which is 239.58. And make sure you add the decimals because sending is silly sometimes.
Thank you about that. Awesome. You do better than I did. Is that like All right, other questions about other homework problems before we go on anything new? We got 5 more minutes to talk about new stuff. But today on the syllabus was dedicated to problem solving, sample problems. I figured we might as well use sample problems that you got to solve anyway. Do you have any other questions? All right, the new stuff. At the end of class last time, there's one on the under the chair. Oh, yeah. I can set up. All right. Can you read it? I don't have that for I think I want to look at it before I do it in front of class. So we'll maybe, if you still have trouble, email me about it. I'll make it. Whatever. I don't have it in front of me. Sorry. Yeah, I'd rather have it practiced before I put it up on the board. So I'll probably make a video of it. You want to? Okay.
Well, I mean, like,
I do want to talk about capacitors. I only have 5 minutes left. I'll make a video about it. Fair enough? Okay. Let me talk about capacitors first. You can have whatever time is left. So at the end of class last time, I talked about 2 plates, 2 parallel plates that are charged up. They're metal. There's a piece of metal, so they're conductive. So you have a conductive plate here. You have a conductive plate there. If I connect those conductive plates up to a battery, it would look something like this. Big metal plate, big metal plate. Battery. Battery. I told you last class that the positive terminal is the long line on a battery, and the negative terminal is the short line on a battery when you have a schematic drawing like this. This isn't a very good schematic drawing. I drew a physical metal plate on one side, a physical metal plate on the other. If this was a more accurate schematic drawing, it would look like this. Battery symbol. Capacitor symbol. But for the time being, we're representing it as what it really literally is. It's a big metal plate on one side, a big metal plate on the other. Now capacitors in circuitry are tiny. But to get the size of the plate right, they take long strips of metal, and they put a piece of paper to separate them, and then they put another long strip of metal, and they roll it up like a fruit roll-up. Truly, it's kind of neat. If you cut one open, I posted a video on the lab page, which I think Dr. Treese shares with you, of somebody cutting one open and unrolling it. You actually see the metal plate separated by a little piece of paper. It's kind of cool. It doesn't really matter what separates them, but the key is they have to be separated. There's no connection between the two. So if I try to send charge through this and out the other side, it doesn't get there because there's some sort of insulating barrier in the middle. The negative terminal of the battery has an excess amount of electrons that it's trying to get rid of. It's negatively charged. The positive terminal wants electrons like crazy. It sucks up electrons with a steady, constant flow of electrons into that positive terminal. So this positive terminal is pulling on electrons as hard as the voltage of the battery implies. It has a 1.5 volt difference in potential, higher than the negative terminal. So that's how much the electrons are getting pulled towards it. The bigger the number, the bigger the pull of electrons towards that positive terminal. 9-volt batteries pull electrons harder. Or that you could also look at it as pushing electrons out, the negative side, harder. If you put them in series with each other, which means you hook one battery up to the next, those voltages add up. So I can get 3 volts by adding 2 1.5 volt batteries right in a row. I can get 9 volts by adding a set of 3 volt batteries, 3 volt batteries lined up, give me a 9 volt. You can stack them just like we stacked the voltaic pile. Same thing happens. Yes?
By stacking, do you mean like when something needs batteries and it needs like 4 double-A batteries?
Exactly. They're put in series. So the positive end of one goes to the negative end of the next, and you just put them in a row. It's interesting to think about putting things in a row electronically, because they don't have to be directly aligned, but the negative terminal of one has to be connected to the positive terminal of the other. That's in a row electronically. So this positive terminal is pulling electrons into it, which means it's got to pull them from somewhere. The only thing attached to it is that metal plate. The metal plate is a conductor, so it gives up its electrons fairly easily. So it's going to start pulling electrons off. And every time it does that, what happens to the charge of the plate? So there's less electrons, which leaves the protons by themselves, which means that becomes positively charged. The positive charges of this create an electric field which pull negative charges towards it. Eventually, it becomes positively charged enough that its electric potential is equal to the potential of the positive terminal. At that point, it'll stop pulling electrons off it because the metal plate will be pulling just as hard as the battery and the electrons will stop moving. But it still wants to pull electrons towards it, and this plate is nearby. So it's going to pull electrons towards that plate. This plate wants electrons because it's near this positively charged object. Lucky for it, it's connected to a negative terminal of the battery. That negative terminal of the battery wants to push electrons out. So electrons are going to come from that negative terminal and get pulled onto this plate. We took too long. I'm almost out of time. The amount of charge on the two plates ends up being equal. You end up with the same amount of charge on both sides. If I disconnect this is the last thing, and then we'll pick up with this next class. If I disconnect this, I cut the battery off. I remove the battery entirely. The charge is going to stay on those two plates indefinitely until I hook it up to something else. That capacitor will hold on to that charge until I give that charge somewhere to go. So I can charge it up with the battery, I can remove it, now that charge is stuck there until I hook that up to something else, some other circuit where it can discharge. That's what we're going to pick up next class. Have a good weekend. Happy Groundhog Day.